Hello, Godoniers! When you make games, you very often have to do calculations in 2D or 3D space to find out in which direction a character should walk, a projectile should fire, or how to rotate a camera when the player moves the mouse. This often requires quite a bit of math, which can be challenging in 2D and gets even more complicated in 3D. So in this video, we are going to explore how we can use transforms to solve a lot of common problems in game programming without being a math wizard. We're going to see how transforms work under the hood and how we can use this information to do things like moving a character relative to his orientation or shooting bullets without calculating a lot of angles and positions. We'll explore how to use transform trees to easily create complex motions like rotating platforms or fanning out cards with very little code. And we will have a look at how transforms work in 3D and how we can use them to easily create first and third person cameras, control the movement of characters, and spawning and moving things in the 3D world. This is a beginner level tutorial. You should know the very basics of the Godot engine, like how nodes and scenes work. We'll also do a bit of scripting, so you should know how to program in the GDScript programming language. Finally, there will be a little bit of math involved, but because we'll let the transforms do most of the math for us, it's enough if you know a little bit about vector math, like adding vectors together and scaling them. There's an example project for this video available on GitHub, so if you would like to follow along, you can download the example project and open it in your Godot editor. You can find a link to this project down in the description. So here we have the beginnings of a top-down 2D shooter game, and in this game the player should be able to move forwards, backwards, left and right, and turn into any direction. Let's quickly implement that. So we add a script to Mr. G here, and let's call it player.gd. Now let's start with the movement. And when something moves, it has a speed, so the first thing we need is a movement speed. And to make this easy to tweak, let's write an export variable for this. So export var movement speed. This is a float, and we start with about 150. And while we're at it, let's also add another for the rotation speed. So export var rotation speed degrees. This is a float, and we start with 180. Now we need some keys that the player can press so our character moves. And we can do this in the input map here in the project settings and input. I have already defined some keys for the movement, so we can see move key bindings for all our 4 directions and 2 bindings for rotating. Well, let's use these bindings in our code. We're gonna need a process function, so let's write one. And now we need to find out in which direction we need to move, depending on which input keys the player has pressed. Godot has a really nice function built in for this, so we can just write var movement direction, and this is input get vector. And now we need to give this function 4 parameters, which are the inputs that map to the x and y axes. Now let's look at Mr. G to see what we need here. So the autocomplete says we need negative x first, and for Mr. G, negative x is backward. So we put move backward in here. Now positive x, which is move forward. And for y, we have negative y, which is move left. And finally, positive y, which is move right. So with this, when the player presses any of the 4 movement keys, we get a vector pointing into the direction that Mr. G should move. So all we need to do is add this to our position. So position plus equals movement direction. Now that was easy, so let's try it out. We start the game. And if I press forward, backward, left, and right, Mr. G moves nicely. Now he's a bit slow, but this is because we didn't yet use our movement speed. So let's fix this. We just multiply this vector with our speed, so times movement speed. And because our speed is given per second and not per frame, we also multiply this with delta, so times delta. Let's try this out. And this works nicely. Great. Next is rotation. And we can do this very much the same. We only have 2 inputs for rotation though, so we need to use a different function. But Godot has us covered, and we can write something like var rotation direction equals input get axis. And now we just need to give it the negative action and the positive action. So in our case, the negative action would be a counterclockwise rotation, so we use turn left, and our positive action would be turn right. And now we can change our rotation very much the same as we did with our position. So rotation plus equals rotation direction. And we also need to use our rotation speed from up here, so times rotation speed degrees times delta. Now, our rotation speed is given in degrees, but the rotation property expects rotations to be given in radians. So we can either convert this value to degrees, or we can just use the rotation degrees property, which allows us to use a rotation in degrees. I think using the rotation degrees property is more readable here, so let's go with that. Okay, so let's give this a try. And if I press the rotation keys, then Mr. G will nicely turn left and right. So we're done, and we didn't even need to do any fancy math. Except that if I now press left, then Mr. G is moving upwards. And if I press backward, he's moving left. Why is that? Well, forward, backward, left, and right are directions that depend on the orientation of Mr. G. And if Mr. G is turned upwards like this, then when I press forward, Mr. G should now move towards negative y instead of positive x. And if he's turned somewhere in between, like this, well then Mr. G will need to move at an angle. Now that sounds like we are going to need quite a bit of math to calculate this. But we can solve this problem very easily with Godot's transform. So what is a transform actually? A transform is Godot's way of encoding position, rotation, and scale. So if we set the position, rotation, or scale of a node, then under the hood, we will actually change a transform. Let's have a look at a 2D transform so we can get a better understanding of what it is and how it works. A 2D transform is a set of 6 numbers, and these 6 numbers control the position, rotation, and scale of any 2D node in Godot. The numbers are arranged in 3 vectors, x, y, and origin. X and y show the direction of the x and y axis. Now let's have a look at these axes first. We can see that the x vector shows the direction of the x-axis. It points 1 in the x direction and 0 in the y direction. So right now it points to the right. The y shows the direction of the y-axis. It points 0 in x direction and 1 in y direction. So right now it points down because in Godot, positive y is down. The origin vector represents a change in position. Let's see how this works with our little sprite node here. Right now, our sprite is at position 0, 0. And this position is used as the origin vector in our transform. So if I move the sprite around, we can see how its position ends up in the origin vector. Great, so we have position sorted out, so what about rotation? Rotation is handled by the x and y vectors. And these 2 vectors together form a so-called matrix, a collection of 4 numbers. This matrix is called basis in Godot. And when we rotate a 2D node in Godot, what we actually do is to change the direction into which its x and y axes point. Right now, the x-axis points to the right and the y-axis points down, as we've seen at the start. But if I rotate the sprite node, we can see that the x and y axes now point in different directions. And there are mathematical formulas to calculate the direction of these axes with a given angle. But the good thing is that all of this math is built into Godot's transforms, so we can just use it for our games and don't need to start calculating sines and cosines ourselves. So if I rotate the sprite to say a negative 45 degrees, the transform internally will use these formulas and we get 0.71 and negative 0.71 for the x-axis, which we can also see here at our red x-axis arrow. And for the y-axis, we get the direction into which our green y-axis arrow is now pointing. So that's rotation. What about scaling? Scaling is also done with the basis matrix. We did rotation by changing the direction in which the x and y axes were pointing, and we can do scaling by changing the length of our x and y axes. So if we increase the length of our x-axis vector, we can see how the image is scaled. And of course, we can do the same thing for our y-axis vector. There's another thing we can do in 2D. Right now, our x and y actors are always perpendicular to each other. But we can actually change this. X and y are just vectors. So we could pick a vector y that is not perpendicular to x. Godot has a setting built in for this, which is called skew. So if we pick a skew of negative 45 degrees, we can see how the angle between the x and y axis is no longer 90 degrees, but rather just 45 degrees. And this looks like we would tilt the xy plane. Okay, that is all great, but how does this help us with our input problem? Well, we just learned that when transforms rotate things, they actually just change the direction in which the x and y axes are looking. I have a little axis visualization here, so let's drag this in as a child of Mr. G, so we can see the axes of Mr. G's transform in-game. Well, let's start the game. And if we now rotate Mr. G, we can see how the x and y axis of his transform change direction. And if we look at the x-axis, we can see that it always points into the direction that is forward for Mr. G. And in the same way, the y-axis always points into the direction that is right for Mr. G. And we can use this to make Mr. G move relative to the direction into which he's looking. Now let's go back into the code. We start with another variable. We call this relative direction. And this is a vector 2. Now, how can we calculate this vector 2? Let's start with forward and backward. And because this is on the x-axis for Mr. G, we need the rotated x-axis from Mr. G's transform. Every 2D node has a transform property which gives us access to the node's transform. So we can type transform.x to get the direction into which the transform's x-axis is currently pointing. So now we have a direction, but we still need to say how much we want to move into this direction. And we can use our movement direction vector for this. For forward and backward, we look at the x component. We can just multiply this with our x-axis from the transform to get the correct movement direction. So we can just type times movement direction dot x. So now if the player presses forward, we get a motion in the direction of the rotated x-axis. And if the player presses backward, we get a motion in the opposite direction of the rotated x-axis. And if the player presses neither forward nor backward, we just get no movement at all, because the direction will be multiplied with 0. Now we just need to use our relative direction variable down here instead of movement direction. And we can start the game and give this a try. Let's rotate Mr. G a bit. And if we now press forward or backward, then Mr. G walks into the correct direction. Now we can go back and do the same thing for left and right. And you probably already have an idea how this is going to look. We can just add the left and right part to our relative direction variable. So we start with plus, and then we pick the y-axis from Mr. G's transform, so transform y. And then we multiply this with the y value from our movement direction vector. Well, let's give this a try. And now we can rotate and move Mr. G into any direction and the input will always be processed relative to the direction in which Mr. G is looking. And because we used the transform's built-in properties, this was really easy to do with no angles and sines and cosines or other fancy math required at all. Now this game is supposed to be a shooter, so it would be really cool if Mr. G could shoot something. Maybe some magic bolts. I've already made a scene for the magic bolt, so let's drag this one in. Now, this bolt will automatically move into the direction it is pointing, and after 1 second, it will destroy itself. Now, let's see this in action. We start the game, and that looks okay, but I think it will look better if we have 3 of these. So let's duplicate it and rotate it a bit up, and then let's duplicate it again and rotate it a bit down. Okay, let's see how this looks. The bolts move into the direction they are pointing and they destroy themselves. Great. Now we want Mr. G to fire these bolts, and for this we need to extend our script. So let's first delete our test bolts and then we can open up the script. Now if we want to spawn a magic bolt, we first need to know which scene contains the magic bolt, and we don't want to hard code this. So let's create an export var bolt scene. This is a packed scene. And now we can drag the bolt scene into our inspector. We also need a button that the player can press to fire a bolt. So let's add a fire action into our input map. So we go to project settings, input. And here we add a new action named fire. And then let's scroll down and add a key binding to it. Or maybe the spacebar. Good. Now we can go back to the code and check for this with if input is action just pressed fire. Now the bolt should always spawn in front of Mr. G, and we already know that where in front of is depends on where Mr. G is located and which direction he's looking. We also want to shoot our 3 bolts into 3 different directions, so we will have to do some calculations to get the correct orientation for each of the bolts. But we can use transforms again to simplify this quite a bit. Until now, we have only used a single transform, Mr. G's own transform. But transforms can also be combined to express more complex transformation. Here we have 2 sprites showing Mr. G, and right now each of them is having the default transform, which does nothing. At the bottom we see a 3rd sprite, and this sprite uses a combination of the transforms of the 2 sprites at the top. In Godot, we use the multiplication operator to combine 2 transforms. So if we multiply a transform with another transform, we get a new transform, which is the combination of the 2 input transforms. Let's see this in action. If I move the first sprite a bit to the right and the second sprite a bit up, we can see that the 3rd sprite's transform is now a combination of both. And this 3rd sprite has now moved both to the right and up. Now it is important to know that the order is important when multiplying transforms. I certainly needed to get used to this because we all learned at school that the order of multiplication isn't important. 3 times 5 is the same as 5 times 3. With transforms, however, this is not always the case. If both our transforms only change the position, then the order doesn't matter. So if I change the first transform to move the sprite up and the second one to move it to the right, then the result is pretty much the same. The 3rd sprite moves to the right and up, just like before. The order does matter when we add rotations. Let's first reset both our input sprites, and now let's rotate the first sprite by a negative 45 degrees, and let's drag our second sprite to the right. And we can now see that our combined transform first did the rotation and then moved it along the rotated x-axis. So we now have Mr. G rotated a negative 45 degrees and moved up and to the right. Now let's reset this again and do it the other way around. So we first move the first sprite to the right, and then we rotate the second one by a negative 45 degrees. Now this gives a different result. Mr. G is still rotated negative 45 degrees, but because we did the movement first and rotated afterwards, Mr. G now ends up just to the right rather than up and to the right like when we multiplied this in a different order. Also, a single transform can represent both a translation and a rotation at the same time. So in which order will Godot calculate these? Well, let's reset our transforms and find out. Now let's rotate this sprite by a negative 45 degrees and then type in some movement on the x-axis. And we can see that this gives the same result that we got when we first translated and then rotated. So a single transform will first translate and then rotate. Okay, now how does this help us with the magic bolts? Well, let's go back to the code and let's start with a few variables that describe what we want to happen. So first we want the bolts to be offset by about 50 units in front of Mr. G. So let's write that down. Or offset, this is a vector 2, and the 50 goes into the x-axis because the x-axis is the forward and backward axis of Mr. G. We also want to rotate the bolts, but for starters, let's just fire a single bolt straight forward. For this bolt, the rotation angle would be 0, so let's write var angle, this is a float, and this is 0. Next, we can create an instance of our bolt. So var bolt, this is a node 2D, and we get this by calling instantiate on the bolt scene. And we need to add this instance to the tree, so let's add it to the parent node of Mr. G. So let's call getParent, addChild, bolt. Finally, we need to set the position and rotation of the bolt. And as I said in the beginning, Godot always uses transforms under the hood. So when we assign something to the position of the node, like bolt position equals something, or the rotation of the node, like bolt rotation equals something, then Godot will just modify the transform of this node. But we can also change the transform directly. So we can write bolt transform equals, and now we can assign a new transform to our node. So what do we use as a transform? Well, we just learned that we can multiply transforms to get a combination of both transforms. So first, our bolt should be at the same position as Mr. G and look into the same direction as Mr. G. So we can write bolt transform equals self-transform. And self-transform is the transform of Mr. G. So now both the bolt and Mr. G are at the same position and look into the same direction. Now we want to do another transformation. We want to move the bolt by the offset and then rotate it by our angle. And we can make another transform for this, so we can write times transform to D, angle, offset. So now this multiplication gives us a combination of both transforms. We first move and rotate the bolt so it is at the same position and orientation as Mr. G, and then we move it 50 units in front and rotate it into the direction it should shoot off. Well, let's try this out. We start the game and fire. And this looks okay. And now let's rotate Mr. G a bit. Fire again. And this works out really nice. And now we can add the two other bolts that spread out to the side. And these really only have a different angle. So let's change our angle variable here to be an array of angles. And we add 3 angles, a negative 45, 0, and 45 degrees. Now we just need to add a loop so we can spawn 1 bolt for each angle. So for angle, this is a float, in angles, and then we can just indent this code, and this should do it. Let's give it a spin. We press space, and we see 3 magic bolts firing. Now let's try if this also works when we rotate and move Mr. G. And this works out nicely. And we only needed a few lines of very simple code. We didn't even need to calculate any positions and angles manually. The transforms did all the work for us. If you've played around with Godot a bit, you probably know already that we can build trees from 2D nodes. Here we have a little setup with 2 truss beams and 3 platforms. And each of these 2D nodes has their own transform that controls the position, rotation, and scale. So I can select this platform and change its rotation. Now these 2 platforms are child nodes of this truss beam. And this is not only for keeping things organized in the tree. In Godot, the transforms of parent nodes also affect the transforms of all of their child nodes. So if I move and rotate this truss beam, the 2 child platforms are also affected by this and will rotate and move with the truss beam. Under the hood, Godot does this by simply multiplying all the transforms from the root to the node to find out where any node will finally end up. So for this platform 1 node, Godot will find all the 2D nodes above it and then multiply their transforms. We have the root node, which is no 2D node, so it will be ignored. Then we have truss beam 1, truss beam 2, and finally our platform 1 node. The result of all these multiplications is called the global transform in Godot. And because we often need the global transform for calculation, Godot provides this transform in the global transform property of each 2D node. So we don't need to calculate it manually ourselves. Now with this behavior, we can build complex movement with very little effort. Let's say we want these truss beams to rotate independently of each other, and we also want the platforms to stay connected to the truss beams and remain upright no matter how the truss beams are rotated. Let's start by writing a script for rotating the truss beams. We add a new script to this truss beam, and we name it rotate.gd. And now we can change the extents line here to node2d, because this script will actually work with every node2d, and we can reuse it. Next, let's export a rotation speed variable that lets us control the rotation speed later on. So export var rotation speed degrees. This is a float, and we start with about 20. Now we can write a process function that does the rotation. We can do this like we did before by changing the rotation degrees property. So rotation degrees plus equals rotation speed degrees times delta. And that's really all we need. Now we can just drag this script to our second truss beam here and maybe let this beam rotate a bit faster, maybe 30 degrees per second. And then we can give this a try. We start the game. And both truss beams rotate, and because the parent's transforms also affect the child node's transforms, the platforms are moving with the truss beams. And we didn't even need to write code for that. That is great, but we would like the platforms to stay upright, so Mr. G doesn't get motion sickness. So let's write a script that cancels out this rotation and keeps the platform upright. So we add a new script to the platform, and we call it keepupright.gd. And we can change the extents line to extends node2d because this will also work with any node2d. So we would need to change the rotation of our platforms to counter the rotation of the truss beams. And this can become quite difficult if we have a tree of nodes like this. Now let's take the platform where Mr. G is currently standing at. This is attached to truss beam 2, and truss beam 2 is attached to truss beam 1. And truss beam 1 is rotated negative 45 degrees. And truss beam 2 is rotated a negative 90 degrees. So to stay upright, the platform needs to counter both these rotations. And if we select the platform, we can indeed see that it is currently rotated by 135 degrees. So all three rotations cancel each other out, and we get an effective rotation of 0. Now, if we want to write a script that cancels out the rotation for the platform, we would need to check all of the parents of this platform and collect all of their rotations so we can cancel them out. But we already know that Godot provides us with this global transform property, which is all the transforms from the root to the node multiplied together. Now to find out how much we need to rotate our platform, we can ask the parent of the platform for its global transform and then get the rotation from there. So in this case, platform 1 would ask truss beam 2 for its global transform. And this global transform will have truss beam 1's negative 45 degrees of rotation combined with truss beam 2's negative 90 degrees. So it will have a negative 135 degrees. And then we can change the local rotation to be the opposite of that. So we can write rotation equals, and then we get the global transform of the parent. So get parent global transform. Then we get its rotation, get rotation. And then we just negate this by adding a minus sign in front of it. Okay, let's give this a try. We start the game. And our platform stays upright. Great. Because these kinds of calculations are really needed a lot in game programming, Godot has an even simpler way of doing this. Every node 2D has the properties global rotation, global position, and global scale. And when we write to these properties, Godot will do the exact same thing that we just did in this line. So if we set the global rotation of a node, then Godot will look at all the parent transforms of this node and then change the transform of this node so we get the desired rotation. Now we want the desired rotation of our platform to be 0. So we can just write global rotation equals 0. So let's run the game. And we get the exact same result with much less and more readable code. So now we can attach this same script to the remaining platforms. And if we run the game again, now all the platforms stay upright and they can all use the same simple script that we used for the first platform. So it can be really useful to think about how we arrange nodes in the tree and how we can use transforms to our advantage. I like to call this arranging of nodes building a node rig, similar to how camera rigs are built to make it easier to get certain shots in filmmaking. And this isn't limited to platformers or shooters. We can also use this in different genres of games. So let's say we want to make a card game. In almost every card game, we want to neatly fan out our cards. We have 3 cards here, so let's try to fan them out manually. So let's rotate this first card a bit to the left and then move it here. And the second card, well, we don't need to rotate, but it should move to about here. And the third card, we need to rotate a bit to the right and move it here. Now, well, that's a lot of rotating and moving, and doing this in code will require quite a few calculations. But we can build a nice rig of 2D nodes so that Godot can do this work for us. If we look at our little card fan here, we can see that these cards form an arc, a part of a circle. So if we give our cards a center or pivot point to rotate around, then we can let Godot do all the translation and rotation for us. So let's first add a pivot node. We press Ctrl A to add a node, and then we just use an empty node 2D for this. And this pivot will be somewhat below the visible part of our scene, so let's put it about here. Well, let's also rename it to card pivot. And now we can drag a card as a child node of this pivot. And then let's reset the rotation and set the card's X position to 0, so it is directly above our pivot. And now if we rotate the pivot node, we can see how the card moves in a nice arc around the pivot. So to fan out some cards, we just need a few copies of this setup. Let's delete these cards and then press Ctrl D to duplicate our little card rig here a few times. And now we can just rotate our pivots here and our cards will fan out nicely. Let's write a little script for this so we can see how this would work. For this script, it would be nice if all of our card rigs are children of a single node, so the script can find them easily. So let's create another node 2D, Ctrl A to add a node 2D, and then let's drag our card rigs as children of this node. Now we can add a script to the node, and we can start writing our code. One thing the script will need is an angle between the cards, so let's add an export variable for this angle. export var angle degrees. This is a float, and we go with maybe 5 degrees. And now we can write a process function to fan out our cards. First, we need to know how many cards we want to fan out. And because all of the card pivots are children of this node, we can just use the getChildCount function for this. So var card count, this is an int, equals getChildCount. And now we can just write a little loop and set the rotation of all of our card rigs. So for index, this is an int in card count. And now we get the child node at this index, so getChildIndex, and set its rotation. Rotation degrees equals angle times index. So with this loop, the first child will be rotated by 0 degrees, the second by 5 degrees, and so on. Now let's try this out. We start the game. And just with these few lines of code, we have nicely fanned out our cards. Now that we have a good idea of how transforms work in 2D, let's have a look at 3D as well. Something that we need in every 3D game is a camera. So let's start with a little script to control our camera here. We add a script to our camera, and I think camera 3D is okay. Now let's first start with moving the camera. First, we need a speed for our camera, and this is something we want to configure. So let's make an export variable for this. Movement speed, this is a float, and let's start with 5 meters per second. And now we can use the same function that we used in 2D to get our input vector. So var movement direction, this is a vector 2, and we call input getVector and give it our backward, forward, left, and right inputs. Great, now we have a 2D movement vector, but we're in 3D now, so we need to translate this into a 3D movement vector. Let's have a look at our camera so we can see how we need to set this up. By default, Godot's cameras look into the negative Z direction, so negative Z would be forward, positive Z would be backward, negative X would be left, and positive X would be right. So let's start with a new 3D vector. Var movement direction 3D. This is a vector 3. And in our 2D input vector, we have left and right in our Y component. So that now needs to go into the X component of our 3D vector. So movement direction Y. Then the Y component of our 3D vector stays 0 because we don't want to move up and down. And for backward and forward, we use the X component of our 2D vector. But because forward is actually negative Z, we need to invert this direction. So minus movement direction dot X. Now we have transformed our 2D input into a 3D direction. We can do the same thing as we did in 2D. We just multiply this with our movement speed and delta and add this to our position. So position plus equals movement direction 3D times movement speed times delta. Okay, let's give this a try. And if I move backward and forward and left and right, well, this works nicely. But when we think back to our 2D movement script, we know that this is going to fall apart once we add rotation to our game. So if I rotate our camera by 90 degrees on the y-axis here in the editor, and we try this again, we can see that the camera now moves right and left when I press forward and backward, and it moves forward and backward when I press left and right. We can again use Godot's transforms to fix this problem very much like we used them in 2D. But first, let's have a look at how 3D transforms work in Godot. 3D transforms are very similar to 2D transforms, but because we add a third dimension, we now need 12 numbers instead of 6 to represent a position, orientation, and scale. We have the same basic setup as in 2D, so our transform has a basis which contains the axis vectors and an origin vector. Because we're in 3D now, we have 3 axis vectors, one for each axis, x, y, and z. And each vector now has 3 numbers instead of 2. Everything else works pretty much the same way as in 2D. So A change in position is encoded by the origin vector, just this time in 3 dimensions. So when I move Mr. G here, we can see how the origin vector now contains the changed position of Mr. G. Rotation is again handled by the x, y, and z vectors, and like in 2D, these vectors hold the directions into which the x, y, and z axes point. Now let's add some visualization of the axes so we can see them better. So right now the x-axis, which is the red arrow, points to the right, and the x vector of our transform shows this. We have a 1 on the x component, 0 on the y component, and 0 on the z component. And the y and z vectors do a similar thing for the y and z axes. If I rotate Mr. G around this z-axis to the right, we can see that the z-axis stays the same. It still points forward, but the directions of the 2 other axes now have changed. The x-axis now points to the right and down, and the y-axis now points to the right and up. And our 2 x and y vectors in the transform show this nicely. And when I keep rotating Mr. G in all directions, the x, y, and z vectors always point into the direction of the rotated axes. Under the hood, the transform will again use a formula to calculate the direction of all these axes. But because rotation in 3D is a lot more complex than in 2D, the formula also becomes a lot more complex. But like in 2D, the good thing is that we don't really need to know about all of this, because Godot's transform will do all the math for us. Let's now look at scaling. And of course, this works exactly the same as in 2D. So the x, y, and z vectors are just made longer and shorter when we scale an object in 3D. So if I scale Mr. G on the x-axis, we can see that the x vector becomes shorter or longer, and similar things happen when I scale on the y and z axes. In 2D, we also had a setting named skew, which allowed us to change the angle between the axes, so they are no longer perpendicular. In 3D, this is also possible, but Godot doesn't have any built-in property for that, like it has for 2D transforms. I have implemented some skewing myself, so we can at least see how it would look. So if I pull this slider, then the Z and Y axes will be rotated towards the X axis, and we can see how this distorts the whole mesh. This is probably not very useful, except if you're making some kind of visual effect, but it's good to know that this still works very much like it works in 2D. Okay, so now we know how 3D transforms are built up, and let's use this to fix our camera movement. Let's reset the rotation of our camera here, and then let's add an axis indicator so we can see which axis points where. Now, when I rotate the camera around the y-axis, we can see that the x and z axes of the camera's transform rotate with the camera. So no matter in which direction the camera looks, the x-axis always points to the right, and the z-axis always points backward. And we can use this to fix our movement. So let's start with left and right, and for this we get the x-axis of our transform. In 2D, we could write transform.x to get the x-axis, but in 3D, we have to write basis.x. This is somewhat inconsistent, but maybe this will be fixed in a future Godot version. Okay, now we have the x-axis, and we can just multiply this x-axis with the left and right value from our input. And the left and right value is in the y component of our movement direction vector here, so we write basis.x times movement direction y. Okay, so let's go back to our scene and let's rotate the camera to say 60 degrees on the y-axis, and let's also hide our axis indicator. Now we can give this a try. And even though the camera is rotated, when I press left, we move left, and when I press right, we move right. Nice. So let's go back to our code and let's also do forwards and backwards. Now for our camera, forwards is the negative z-axis. So we need to add the negative z-axis multiplied with the forward and backward part of our movement direction vector. So plus negative basis z times movement direction x. And we can simplify this a bit and remove the parentheses. So we end up with minus basis z times movement direction x. Okay, let's try this out. And this works nicely. Now we also would like to rotate our camera so we can actually walk around in our world. Now let's do rotation with the mouse. So we first need to find out when the mouse has been moved. And to do this, we can listen to Godot's input events. So let's write an input function. And we're only interested in the mouse movements. So let's leave this function immediately when the input event was not about a mouse motion. So if not event is input event mouse motion, then we return. Now, how do we find out how much the mouse has been moved? Well, let's control click on the input event mouse motion to check the documentation. Let's see which properties do we have. We want to know how much the mouse has moved. So relative sounds like it could do what we need. Well, let's read the description. It says the mouse position relative to the previous position. Well, that is exactly what we need, so we go with that. Let's first extract this into a separate variable. So var mouse movement, this is a vector2, and this is event.relative. Good, now we know how much the mouse has moved, and we can do the rotation. Let's start with rotating left and right. Which axis do we need to rotate around for this? Well, let's have a look at our camera. If I rotate the camera left and right, it rotates around the y-axis. And to rotate left, we need to increase our angle. And to rotate right, we need to decrease our angle. So let's go back to our code and rotate the camera around the y-axis. Because we're in 3D now, rotation isn't just a single number anymore. So we cannot simply assign something to rotation degrees as we did in 2D. But Godot has a nice set of helper functions on 3D nodes which can help us with rotating around the axes. So to rotate around the y-axis, we can call rotate y. And then we tell this function how much we want to rotate around the y-axis. We want to use our left and right mouse movement to determine how much we want to rotate. And this is in the x component of our mouse movement vector. So if we move the mouse left, x will get negative. But we just saw that to rotate left, we need to increase our angle. So if we want to rotate left, when we move the mouse to the left, then we need to invert our mouse movement. So we need to write rotate y minus mouse movement.x. Now, in many games, the player can actually configure whether or not the mouse movement should be inverted. But because this video is already quite long, we'll just hard code this for now. Well, let's give this a try. And things rotate way too fast. Why is that? Well, the rotate y function takes an angle in radians, but our mouse movement is a distance in pixels. So we somehow need to convert our mouse movement into an angle. Well, let's say 300 pixels of motion should be half a turn. So we can divide our input by 300 to get the amount of half turns. And every half turn in radians is pi. So we multiply this whole thing with pi. The 300 here is our mouse sensitivity. And in a real game, this should also be configurable, but we'll stick with the hard-coded number for now. Also, I think it is really distracting if the mouse cursor is visible, so let's capture the mouse cursor when the game starts. We add a ready function, and in there we capture the mouse, so input mouse mode is input mouse mode captured. Good, let's try this out. And this works a lot better. now we can actually start walking around, and if we turn our camera in-game, then we will still walk into the correct direction because we use the transforms axes to do our movement. Nice! So now we also want to be able to look up and down. Well, this should be quite easy to add. Let's look at our camera again. So if we want to look up or down, we need to rotate around the x-axis. And we need to increase the angle if we want to look up, and decrease the angle if we want to look down. So in our code, we can just duplicate our rotate Y line here, but instead of rotating around the Y-axis, we now rotate around the X-axis. And instead of taking the horizontal mouse input, we now take the vertical mouse input. Now we have duplicated this mouse sensitivity code, which isn't really great. But because this applies to both axes of our input, we can just move this divided by 300 times pi part up here where we create our motion vector, and we can remove this duplicated part from our lines. Great, let's give this a try. And well, this isn't working at all. When I move up and down, the camera tilts, and this is not the way this should work. So now that is weird. Why isn't this working? Well, let's have a look at our camera. Here in the transform section, we have a property called rotation order. And if we hover over it, the description reads, specify the axis rotation order of the rotation property. The final orientation is constructed by rotating Euler angles in the order specified by this property. So what are Euler angles and why do they break our rotation? Well, Euler angles are another way of expressing how an object is oriented in 3D space. They're named after the Swiss mathematician Leonhard Euler, who came up with this concept. When we use Euler angles, we tell Godot 3 angles for the x, y, and z axis, and then Godot constructs the final orientation by rotating the object around each of these axes. But in which order are these rotations applied? There are 6 ways in which this can be done. We could first rotate around x, then around y, and then around z, but we can also choose any other order. And by default, Godot uses y, x, z order, so first everything is rotated around the y-axis, and then x, and then z. This works pretty much like a gimbal works in the real world. This is a gimbal using Godot's default rotation order. So we first rotate around y, then we rotate everything around x, and finally everything around z. Now that is really easy to understand, but it has quite a few problems. The first problem is that every rotation affects every other rotation. So say I set the y rotation to a negative 90 degrees, and now I change the x rotation. Now we can see that Mr. G now tilts, which is exactly what we saw in our game as well. Also, in our game, we really want the y-axis to stay upright all the time. But if I set the x-axis rotation to a negative 45 degrees, this will tilt our y-axis. And if I now change the y-axis, then Mr. G will rotate around this tilted y-axis. And this may be okay for a space game or a flying simulator, but when we do a game on the ground, like we do, we actually want Mr. G to rotate around the y-axis that is perpendicular to the ground, like this. A third problem with this approach is a phenomenon called gimbal lock. If I set the x-axis to a negative 90 degrees, then suddenly changing the y-axis and changing the z-axis do the exact same thing. With this setup, there's no way to rotate Mr. G this way. To make this work, we would need to change the z-axis to 90 and the y-axis to negative 90, and then we can rotate around the x-axis. So using Euler angles to control our camera really isn't the way, because we would need to do a lot of calculations and checks to get the exact movement that we want for our game. And we'd also need to take care that we don't get into a gimbal lock situation. But it is still very nice to be able to control rotation by just changing a single number. So is there a way to keep things simple, but without getting these problems? Well, earlier when we were looking at 2D, we built ourselves a rig. So Godot would do all the math for us. And we can do the same thing in 3D as well. So how would a rig for our use case look like? Well, we want 2 rotations that should work independently of each other. And we will need 2 transforms for this. So let's add 2 node 3Ds to our scene. So Control A to add a node, and we select a node 3D. And then Control D to duplicate this node. Now we can start building our rig. The first node should control our left and right rotation. So let's call this one yaw. And the second node should control our up and down rotation. So we call this one pitch. Because the yaw node will also tell us which direction is forward, we make this node the root node of our rig. Then we make the pitch node a child of the yaw node and the camera a child of the pitch node. Well, let's reset the rotation of our camera, and now let's try the rotation. So if we rotate our yaw node around its y-axis, then the whole rig will turn around y. And now the pitch node. And well, this isn't what we need. The camera rotates around a pivot at the ground, but we want it to rotate around a point that is roughly 2 meters above the ground. To fix this, let's first reset the translation of the camera. And then instead, let's move the pitch node 1.9 meters up. Now, if we rotate around the x-axis of the pitch node, then everything looks the way it should. Okay, so now we only need to make this work in the game. Because now our script doesn't only control the camera, but a rig of nodes, I think it's better to move this script to the root of our rig, which is the yaw node. So let's remove the script here from our camera and instead drag it onto the yaw node. Because our new node is no longer a camera 3D, we need to change the extends line up here. So this is now extends node 3D. For the movement, really nothing changes, so we can leave that part alone. The interesting part is the rotation. For this, we need to have access to our yaw and pitch nodes. So first the pitch node, let's make this a scene unique node, and then we can control drag this in. Now the yaw node, and the yaw node is the node where this script is currently attached, but I still would like to make a variable for this so our code is a bit easier to read. So let's just drag this node in as well. And we can just change the assignment here from this node path to self. Okay, and now we just need to change our rotation code a tiny bit. So we go down here. And the left-right rotation will be done on the yaw node. So we write yaw rotate y. And the up and down rotation will be done by the pitch node. So we write pitch rotate x. And that should already do the trick. So let's give it a try. First, let's try to rotate left and right. And that works nicely. And now up and down. And that also works nicely. And now let's try to walk around a bit. And that works as well. Great. So now this rig not only makes it very easy to control our camera movement, we can also turn this whole setup into a third-person camera with absolutely no changes to our code. For a third-person camera, we need a player model, so let's drag in a model of Mr. G here. And we make Mr. G a child of our root node, so he moves with the rig. Let's also reset the position, and let's drag the model up and rotate it 180 degrees around the y-axis, so the model looks where forward is. Okay, so now how do we make a third-person camera? Well, it's really simple. All we need to do is pull our camera node about 3 meters back. Now, if we rotate our yaw node, we can see that the camera orbits around Mr. G. And if we rotate our pitch node, the camera tilts up and down around the pitch node. Well, let's try this in game. And this works really nice. So with clever use of transforms, we got a camera that can do first and third person in a single script with very little code. There is a little problem though. Mr. G really just is a 3D model, so he can walk right through the trees. But of course, he should collide with the trees, so we will need to use a physics body like a character body 3D rather than a simple node 3D. But can we still use our transforms with a physics body? Well, let's try it out. So let's right-click on our yaw node and select Change Type. And we change this to a character body 3D. We also need to add a collision shape, so the physics engine knows how big Mr. G is. So Ctrl A to add a new node. And we add a collision shape 3D. And as a shape, let's go with a simple sphere shape. The sphere should go around Mr. G, and that looks about right. Now we need to change our script so it works with the character body. So first let's change the extends line to extends character body 3D. And now when using a character body, we don't change the position of this body ourselves. Instead, we set a velocity vector which tells the character body into which direction we want to move, and then we call move and slide. Then the character body will do all the physics calculations and move itself. The good thing is that we already have calculated our desired velocity. Simply speaking, velocity tells us how fast and in which direction an object changes its position. And this line is doing just that. So we can just change position to velocity here and remove the plus. The only difference is that the character body expects a velocity in units per second. But because we multiply with delta, we currently have a velocity in units per frame. So we don't want to multiply our velocity with delta here, so let's delete this part. And now we only need to add a call to move and slide, and this should do the trick. Well, let's start the game. And now Mr. G properly collides with the trees. So we see that even if we use physics bodies, we can still use the power of transforms to do all the math for us. As a last thing, let's also add some magic bolts to our game, like we did in 2D. I have prepared a magic bolt for 3D, which works exactly like the 2D one. It will move forward and destroy itself after some time. Well, let's start the game. And we can see how the bolt moves forward and automatically destroys itself. Okay, so how can we spawn a bolt at a good position with the correct orientation in our game? We could do it like we did in 2D when we did some calculations with transforms in our script, but in 3D, most of the time we will have a spawn position that somehow depends on our 3D model. Let's say I want to spawn 2 bolts where the hands of Mr. G are. Now, we could measure out where the hands are and then calculate some translations and rotations in our script, but it's much easier to just use our rig for this. So let's add a marker 3D node to our rig. Ctrl A to add a node, marker 3D, and let's call this one right hand. Now let's find a good position for this. Maybe we make the bolt a child of this marker 3D so we can better see what is going on. And now we move the marker node where we want the bolt to spawn. And this looks about right. Great. Now we just need to duplicate this for the left hand. Ctrl D to duplicate, rename this to left hand. And let's move this over here to the left hand. This looks nice. We can get rid of the bolts and start to write the code for firing the bolts. This works a lot like it does in 2D. So first our script needs to know which scene should be spawned, and like in 2D we make an export for this. So export var bolt scene, and this is a packed scene. Now we can drag the bolt into this export field. Then we need our left and right hand markers. So let's make these scene unique nodes. and control drag them into our script. And now we can do the firing. Let's first check if the player has pressed the fire button. So if input is action, just pressed fire. And then we want to spawn bolts at both the left and the right hand. Because the code for these will be the same, let's create an array with our spawn points. So for spawn points, this is an array of node 3Ds. And we initialize this with left hand and right hand. Now we can just walk over this array and spawn a new bolt. So for spawn point, this is a node 3D in spawn points. We make a new bolt. So our bolt, this is bolt scene instantiate, and we add it to the scene. So get parent add child bolt, just like we did it in 2D. Now we need to properly rotate and translate our bolt. And with our transforms, this is really easy to do. Our spawn points are the left and right hand nodes, and we know that these are already properly rotated and translated because they are children of our rig. But we cannot just use their local transform, because this local transform only contains the positioning of our hands, but not the rotation that the rest of the rig is doing. But we learned that all nodes also have a global transform, which is a combination of all the transforms from the top to this node. So all we need to do is to set the global transform of our bolt to be the same as the global transform of our spawn points. So bolt global transform equals spawn point global transform. So let's try this out. And if I press fire, we can see how the bolts are created at our spawn points and move into the direction that Mr. G is looking at. And I can walk around and rotate Mr. G, and the bolts will always spawn at the correct position and orientation. And we only needed very little code that is very easy to read and understand. In this video, we explored how transforms work in Godot and how we can use them to simplify a lot of common tasks in game development. We learned that Godot internally uses transforms to represent movement, rotation, and scaling of all 2D and 3D nodes. We learned that transforms consist of a basis matrix and an origin vector. We learned that the basis is built up from 2 or 3 vectors that point into the direction of the x, y, and z axes. We learned that rotating and scaling an object changes the direction and length of these basis vectors, while moving an object changes the origin vector. We learned that transforms can be multiplied with each other, and that the result of this multiplication is a new transform that combines the transformation of both input transforms. And we learned that Godot's nodes do this automatically when we build node hierarchies. So when we move, rotate, or scale a parent node, then the child nodes will be affected by this change. We learned that we can use this behavior to build node rigs that make it very easy to control complex motion from our code, like keeping 2D platforms upright or fanning out cards in a card game. We learned that using these rigs to do rotations in 3D is simpler and more powerful than using Euler angles because it avoids problems like Gimbal lock and gives us more control. We also learned how we can use information from transforms to drive physics bodies like a character body 3D. I hope that this introduction to transforms in Godot has been helpful. If you have any questions or want to share some neat transform tricks that you discovered, please post them in the comments. If you liked this video, please give it a thumbs up and maybe consider subscribing to the channel to get notified when new videos are posted. Thank you very much and happy Godoniering!